Hello and welcome back. In this video we will look at variational autoencoders, which are a class of generative models that provide a principled way to sample from the data distribution or the model distribution. It is a brief outline of our talk in this video. So, we will start off with some introduction to autoencoders and what is meant by latent vectors or latent space, and then we will move on to variational autoencoders, and finally we will conclude with variational inference, which is a probabilistic interpretation of VAEs. So, in this video we will primarily focus on how variational autoencoders are used in a deep learning context. So, we look at autoencoders. So, they are a class of neural networks which are trained to reconstruct their input. So, if you are thinking of images as input, typically most generative models seem to have a lot of applications in the computer vision or image or using images. So, let us say input data is some image, let us say MNIT data set 28 cross 28 image, and the idea behind this neural network is to reconstruct its output. So, the output will be another image which is 28 cross 28, and the optimization in this case proceeds by making sure that your reconstruction and your input are consistent with each other. In the sense reconstruction loss is minimized. The typical structure for a autoencoder is basically the input. You can think of if you think of it as a fully connected neural network or an MLP, then you would rasterize the 28 by 28 image for 784 pixels, and then you will have a successive layers with a decreasing number of hidden neurons. So, we come to a layer where which you call the bottleneck layer, and from there we have again a successively increasing number of hidden neurons in every layer till we get to the output, which is the same size as the input layer. Now, this layer from which the output is reconstructed, it is called the we can call it the representation or the latent space. Okay. So, we will denote it by Z. Okay. So, the idea behind using autoencoders is to obtain a reduced dimensional representation of your input, in the sense that it retains most of the significant variations in your input enough to reconstruct it. So, that is the whole idea behind training these autoencoders. However, there is no structure to the, it is very hard to impose some structure to the Z that we estimate. So, typically you would have some sparsity constraints and things like that, so that there is you get some meaningful representations, but otherwise it is difficult to impose some structure in Z. So, what VAEs do is to take this a little bit further. In fact, the names are similar of the names are similar and the connection is very superficial, because we can see that, as we will see later, VAEs come from probabilistic arguments which are much more structured and leads to a more meaningful Z. So, this Z, as I mentioned earlier, it is referred to as the latent space or a latent vector, which is what we are trying to infer. So, what does this give us in terms of advantages? Okay. So, first that the latent space or the latent vector that we estimate is basically reduced dimensionality. So, in the case of images, if you have very large images, maybe it is possible to get a latent space representation which is only maybe 2 or 3 parameters, okay, or maybe hundreds of parameters instead of millions of parameters when you are thinking of natural images. And what do we do with this latent representation? The idea is this latent the representation is can be actually used to create new images or generate new data by sampling randomly from it. So, what we ideally want is a probabilistic or a probability density function for your Z, so that we can sample from it, and from there we can generate images which are close to the training data that we used. Okay. So, for instance, let us look at digit generation, right. So, we have training data X of MNIST digits, these are 28 cross 28 images, there are 60,000 of them, and our purpose is to generate digits like X, but not really the same ones found in the data set, right. So, which is like saying we want to maximize this likelihood P of X. That is typically what we want in a generative model. We want a probability model of our input data. So, what would be a latent structure or latent space represent? So, in this case, these are things that we are unable to observe. So, we only observe once a person has finished writing. So, we do not know what are the different strokes that he would have used or he or she would have used, and there are also other things like the orientation, bigger, how big a font, how thick are the strokes, so on and so forth. These are some of the latent structures or the latent space involved in the output that we see, which is basically the digits. The finally that is the observation that we make, is the digit itself or the image of the digit itself, but what went on to creating it we do not know. Okay. So, what we are trying to do is to model that latent data. So, basically we model that as in the form of a latent space from which we sample this vector z. Okay. So, z is a random vector usually with lesser dimensions than that of the input data, and what we also want is a distribution for z. Okay. So, we can have a prior distribution for z, okay, from which we can sample z, and we can also define a posterior distribution, and this is what most people are interested in, that is, given this data set what would be the most likely z values that we can have. Okay. So, once we have this distribution, then we can sample this z from that distribution and map it to samples x. So, that is the idea behind variational autoencoders, okay, is to infer this distribution p of z given x, so that we can use that to sample from a model distribution x. Okay. Basically, as I mentioned earlier, the idea is to map training data, in this case input images, to a latent space using a neural net. Okay. And the latent space is basically the z, which is posterior distribution p of z comma x. So, that is the p of z comma x, z given x, sorry, and the prior distribution, we have some assumptions about the prior distribution, and we usually model them as Gaussian distributions. Okay. The output of the network, which provides p of z given x, basically it does not exactly give you samples from p of z given x. Instead, it gives you, since we have parameterized it as a Gaussian, it gives you two parameters, basically the mean and covariance value of the distribution. Okay. Now, we draw a random sample from the latent space. So, once we know the mean, so we would know mu, and we also know the covariant matrix. So, given this information, we can sample z from this latent space and use that to generate data which is similar to your training data x. Okay. So, how is that done? So, again not very surprising, we will use another neural network which will sample from mu comma z, take that as input and map it to an output which is very similar to your input data or input images. So, if you take MNIST digits, you would map from your sample of latent vector to a digit which looks like it came from the training data distribution. Okay. Of course, you can also interpret the output of this network, the network that takes p of z given x and gives you a sample from the training data similar to the training data distribution, and we would like to if we interpret our output again as as the sample from a Gaussian distribution, then it leads to a reconstruction loss. We see how that is done in the next few slides. So, variational encoders consists of these three components: the encoder, decoder and a regularized loss function. Okay. So, this is from a deep learning point of view. So, as we saw earlier, encoder takes training data as input and provides you with the parameters of the latent space distribution, and the decoder takes a sample from the distribution, decoder from the latent space distribution, and provides you with the output which is similar to the data in the training data. Okay. And these two are basically parameterized. The encoder and decoder are both deep neural networks, right. So, we can use them. Okay. They can be convolutional neural networks or just fully connected ones, you can use either of them. So, typically for images you would make sense to use a convolutional neural network. Okay. And we have a regularized cost function, we will see what that is in order to optimize the parameters of this neural networks. So, the VAE architecture, so this is your training data as input, so training data samples are given as input, skew of z given x is actually represented by a neural network. So, the phi are the parameters of the weights, parameters or weights of the encoder, right. and it gives you output z. In this case again slight abuse of notation, it does not exactly, you do not exactly get z, but you would get the parameters because they are dependent on x. Okay. So, for every x that you give as input, you have a corresponding mu and sigma coming for it, and you have this decoder which is again a neural network. The theta are the again the weights or the, I will write down weights instead of parameters, weights of that neural network, which takes, which samples. So, this is sample using mu and sigma, right. You sample using mu and sigma and get a z which is given as input to this neural network, and it provides an output x which is a sample which is similar to x tilde, which is sample which is similar to x. Okay. So, in this case we have given a particular x as input from which we have sampled a z, right, and so we would expect the output x tilde to be the same as x tilde to be the same as the x that we gave as input over here. Okay. So, this is the VAE architecture, and in order to train this we have a cost function which consists of two parts. We will look at what they are, and that ensures that this the whole network is consistent in terms of a particular z giving rise to a particular sample from the training data. Okay. So, the VAE loss function consists of two terms. Okay. So, this is your data reconstruction loss, this is typical in most networks, and this is your regularizer. Okay. So, if you look at the regularizer is nothing but the KL divergence. So, what are the KL divergence between the distribution that is output by the encoder network and your prior model for the distribution of z. So, we are actually in this case, in the case of VAEs, both of them are modeled as Gaussian distributions. Okay. So, the KL divergence, if you recall, it tells you how similar two distributions are. If they are exactly the same, then you get 0. Okay. So, that is the optimum value that you get for that distribution. So, the sum of these two is what you optimize. So, let us take a closer look at each one of them. So, as I had said earlier, so q phi of z comma x is the output of the encoder. So, which gives you two, in this case we have modeled them as Gaussian. So, you will get a mu and sigma corresponding to a Gaussian, right. Peak theta of z is another Gaussian, right, with 0 mean and unit standard deviation. Okay. Again, if you look at the covariance matrix, it is constrained to be diagonal. Okay. And so is this one, the identity matrix. So, our prior for z is basically a standard normal distribution, and we constrain the output, the parameters of the this posterior distribution q of zx, which is output by the network whose parameters are phi, are again interpreted as the mean and covariance matrix of a Gaussian distribution, of course, with the covariance matrix being constrained to be diagonal. Okay. Now, this is your reconstruction loss. Look at it. So, this is the output of the decoder, right. The output of the decoder, it is actually an image that it outputs. In this case, if you are looking at image, looking to generate images. Now, if we assume that this distribution, that the if you interpret the output also as the mean of a Gaussian distribution, then you can again once again model the output as the parameters of the Gaussian distribution, wherein the mean is given by the output of the network characterized by theta. Okay. So, if you take the log of that, then you will end up with the usual least squares loss function. On the other hand, if you are looking at let us say binary images wherein the pixel values are 0, 1, then you can also use binary cross entropy. Binary cross entropy between your input image, where the pixel values are either 1 or 0, and the output of the decoder with values ranging from 0 to 1, which is done by using a sigmoid at the output. Then you can interpret each of the output pixel values as probabilities drawn from a Gaussian, and which we can use either as a if you take the log of that, then you get the usual least squares loss function. On the other hand, if you treat the pixel values as binary variables themselves, and you can still use the cross entropy, okay, that which comes from the Bernoulli distribution. Okay. So, each of these are possible. So, we have a combination of two loss functions. One is the reconstruction loss, and the other one corresponds to the constraint on the output of the encoder, making sure that the parameters correspond to that of a standard normal distribution. So, that is the regularization that we impose. Okay. So, this is from a deep learning point of view. Once again, this is essential because you can say, well, since you are constraining it to be drawn from a standard normal distribution, why do we even need the encoder network, right? So, you can always say I will just draw from Z, and then I will try to reconstruct some arbitrary x. So, the idea behind doing this is that we want to make sure not all Z will give rise to the x that we have in our training data. So, we specifically want to work with Z, the vectors that we are now using as hidden representations or latent space representations, to correspond to the data samples in our training data. So, we have an encoder network that takes a particular x from our training data distribution and maps it to a Z, and we try to reconstruct the same x using the decoder from the Z that we have obtained. Okay. Now, the cost function to be optimized, the cost function to be optimized has to be done on a image by image basis. So, in the sense there are two ways of looking at this. One is how do you let's take a look at this cost function. So, once you pass through the once the encoder has given you a particular mu and sigma, then you can sample a lot of Z values from that mu using that mu and sigma, pass it through the decoder function to reconstruct, and of course, the expectation values will be over all the Z values that you generated for that particular x. Now, as I mentioned earlier, this becomes slightly harder to do because you have to sample a lot of Z, because not all Z that you sample will correspond to the x that you have at hand. So, to make this thing simpler, so we have the encoder function. So, the expectation value can be done over, for the loss function can be done over all the samples in your training data. So, the way it works is, if you have the training data, let us say a mini batch or the entire training data set, you will pass it through the encoder to obtain mu and sigma. You will sample a Z from each of the outputs corresponding to every x of the encoder, and pass it through the decoder to get the reconstruction loss, so that we can do back prop on that cost function. Okay. There is still one problem left, because the sampling function per se, it is not a differentiable function, right. You cannot differentiate the sampling process. So, there is a workaround called the reparameterization trick. We will see what that is. So, just to recap briefly, this is the image is what we on the left is what we looked at. So, we have an x, this is a bunch of x, that is samples from the training data, goes to the encoder, gives you parameters of a Gaussian distribution from which you sample a Z, right here, then you pass it through the decoder, which will give you a reconstruction of your input. Okay. So, then you have a sum of two cost functions. This is what we saw earlier as the data reconstruction loss, and this is to constrain, this is the regularizer which makes sure that the parameters that you are generating from the encoder remain close to the unit normal distribution. Now, doing it this way, so we want to backprop through the entire network all the way. So, but that is difficult to do so through the sampling process, because the sampling itself is a non-differentiable function, right. So, to alleviate this, the reparameterization trick, what it does is it uses a standard trick, right. So, if you have a sample from a standard normal distribution, you can convert it into a sample from a Gaussian distribution with a particular mean and standard deviation. That is what is exactly done here. So, everything else remains the same, the usual encoder x goes to the encoder to give you mu and sigma, but you sample epsilon. For every x you will sample an epsilon from a unit standard normal distribution, right, and then you would do the trick of multiplying by sigma and adding to mu to it, right, and that is given as input to the decoder. Now, backprop can go through the entire network in order to update all the weights. Okay. Since this particular this process of sampling sigma from n0y do not depend on the parameters of your either the decoder or the encoder. Okay. So, once you have trained to the entire data set, what is it we do with it? How do we let us say how do we generate samples? So, that is very simple. All you do is you sample from the standard normal distribution. Since we have constrained the encoder or regularized the encoder to be that way, you can sample some z from the standard normal distribution. You can get rid of the encoder, you can discard this, just have, because now we have got z, you know where to sample z from, and you just have to put z through the decoder, okay, and it will provide you a sample. Now, how is this? We earlier looked at autoencoders. So, the similarity is the following: both of them have a encoder and a decoder. We saw that. So, we take the classical autoencoder takes as input your training data samples and successive hidden layers. There is a bottleneck layer which is treated as a hidden representation, and that hidden representation is then mapped back to your input. So, which is exactly what happens here. We have this Q which maps x to z, that is the bottleneck layer in your autoencoder, and then you have the decoder which takes as which input your hidden representation and provides you with the output. Okay. So, this structure is why it is called an autoencoder, otherwise the principles are different. Now, the advantage behind doing it this way is that is making the output of the encoder stochastic, right. We are not treating it as some deterministic value z, but rather treating it as the parameters of distribution from which z is to be drawn. Now, this provides some interesting results because it provides meaningful or a structured z representation, in the sense that if you sample close to some of the z values that are estimated for the x training data x, you will get similar x, right. And if you systematically sample z over the range of z values that has been generated using this network, then you can see that they have mapped to some attributes in the images that you are using. Okay. It will not be exact, but it gives you a very smooth transition. As you change z gradually, the images will also transition smoothly. Okay. So, there is the structure of the images can be captured in the distribution of z, rather than providing some arbitrary hidden space representations or latent space representation. You have a very structured z that comes out of this process, and that is made possible by treating the output of the encoder as stochastic rather than as a deterministic hidden layer in autoencoders. Okay. Another point is that the cost function that we derived from the point of view of deep neural networks, if you go back to what we saw earlier, we have the sum of these two terms, right. So, this we wrote down as a data reconstruction loss plus a regularizer. Okay. So, that is from a deep learning viewpoint. However, it is actually possible to derive this cost function from probabilistic arguments. So, starting from trying to maximize your the likelihood of your data, it is possible to derive this particular cost function to be optimized. So, this is a much more principled way of creating a generative model. The innovation here is that the outputs of the generative model, in the sense this P of z comma x, z given x, sorry, those are the parameters of the distribution, that has been replaced by a neural network. So, the parameters of P of z given x, this PDF has been replaced with a neural network, which basically regresses your mu and sigma of your P of z comma x. So, mu and sigma corresponding to P of z comma x are regressed by your neural network. Similarly, the process of mapping from z, which you have sampled from P of z comma x, to data, the data that we actually want to get, the generated data, is also accomplished using a neural network. This provides you great advantage because neural networks can pretty much learn very complicated functions from higher dimensional space, because the inputs to, for instance, if you take the input to the encoder, let us say it is a picture, it is an image, it is a let us say 100 cross 100 image, that is a it is like 10,000 dimension of 10,000, right. So, your 10,000 input dimensions can be easily handled by a neural network. It provides a structure to do that, it is a nonlinear function mapping. Similarly, from mapping from z to x is again this function as it is denoted here, that is also made possible by the neural network. So, the f here represents the neural network, and the p and the q are the probability distributions. Okay. So, we have parameterized the probability distribution as Gaussian, and we have estimated the parameters of the Gaussian using neural networks. So, this is the strong point of this variational autoencoder, in addition to having a principled way of obtaining the cost function. So, which means that the z's that you generate from your training data are meaningful. This is not possible in, let us say, using a classical autoencoder, because the only thing you can do is possibly make it sparse to have a good representation. But in this case, varying z smoothly, as many papers have shown, which we will refer to later, varying z smoothly can give you variation of your input. Okay. So, that is the advantage of using variational autoencoders. So, to summarize, the encoder is a neural network, that here the encoder is a neural network that transforms the input image into parameters of a Gaussian distribution. Okay. And this Gaussian distribution corresponds to the latent space, and so we had the mean and k covariance corresponding to the latent representation, and we regularize it by making it close to a unit normal distribution. So, that is how we regularize the network. Now, we randomly sample from the latent distribution, and we assume that z generates the image input image, at the input to the encoder. When I say input image, it is an input to the encoder. Then we send that z through a decoder, which is again another neural network, it is a function mapping, which transforms that z into the input image. Okay. And we optimize, of course, in order to optimize we do the reconstruction loss, that is make the output of the decoder as close as possible to the input image to the encoder. So, doing this process over your given input data trains your decoder appropriately. So, once the training is done, you can discard the encoder if you want and just sample from a standard unit normal distribution, pass it through the decoder and obtain samples of data that you want to generate.